This video is about projectiles that are launched at angles. So far we've only dealt with projectiles that were launched horizontally, but now we're going to add in this idea where it's launched at some angle, either upward or downward, and the example today is upward. Let's imagine that we have a soccer player named Pat. Pat kicks a soccer ball at an angle of 30 degrees above the ground at a speed of 25 meters per second. That's about 50 miles an hour. I think that's possible. Find the ball's maximum height, the time of flight, that is the total time it's in the air from the ground till it hits the ground again, and the horizontal range. This question with different numbers will be on your next test. Okay? I expect you that by the time we've done this example and you've done a couple more in class and some other ones that are very similar, that you should be able to do these three things: to find the maximum height, the time the ball's in the air, and the horizontal range. So we're kicking that ball at 25 meters per second at an angle of 30 degrees with the ground. How is this different from our other problems? Well, one, there's an angle, and two, there is an initial vertical velocity. If you launch things horizontally, the initial vertical velocity is 0. But now that's not the case. This ball leaves Pat's foot with a speed of 25 meters per second. Part of it is vertical. Part of that speed is vertical. So here's how we're going to set this up. We'll do a similar process to what we did in the previous examples, in the previous work with projectiles launched horizontally. We'll draw a sketch, but we're going to add some things to our sketch that we didn't have on there before. We're going to label a lot of velocities on our sketch. So I've drawn the sketch and the trajectory, here in green, of the soccer ball. And I've labeled the information that I was given in the question, which is 25 meters per second is the speed at an angle of 30 degrees with the horizontal. But now I want to also label the velocity components at those positions. So initially, the ball is moving sideways and up, so to the right and up. And we'll say right and up are both positive, and let's make down and left both negative. It's very important to do that, especially if things are moving up and down in the same problem. So part of this velocity is horizontal, and we learned how to calculate the magnitude of that horizontal velocity. Remember, that's using the cosine. So I'm going to draw that, and then I'm going to label it 25 times the cosine of 30. So that much of the velocity is horizontal at the beginning. And the vertical component, I'm going to draw over here, is 25 sine 30. So it turns out that if maybe you remember, maybe you don't, doesn't matter, the sine of 30 is a half. So 12.5 meters per second is that vertical speed, and something slightly less than 25 something is 25 cosine 30 is the horizontal speed. You can go ahead and multiply those. You can punch in cosine 30 in your calculator, multiply it by 25, and put that number down. But you're going to get a whole lot of digits. And instead of writing dot, dot, dot down all the time, and trying to write those digits down, I'm just going to leave it 25 cosine 30. These are the initial vertical and horizontal speeds. But what's the vertical speed at the top of the path? What's the vertical speed? Well, momentarily, just as that soccer ball gets to the very tip top of its path, its highest point, it's run out of vertical speed, right? So as it goes up, this vertical vector gets smaller and smaller and smaller and smaller because gravity is slowing it down. So the vertical speed at the top, I'll call that Vy. I'm not going to draw a vector because it's 0, is nothing. It's not moving up or down at the very tip top. But it is still moving horizontally. Remember, gravity doesn't affect things that are moving sideways any differently. So the acceleration due to gravity is the same. And horizontally, that has no effect. So our horizontal speed is still 25 cosine 30. That horizontal velocity never changes the entire way up and down. It's always constant. Nothing's pushing it sideways once it leaves Pat's foot. At the very end, and I'm going to slide this across just so you can see it. At the very end, that horizontal velocity is still there. That is 25 times the cosine of 30. But now we also have a vertical velocity. Now, many students get caught in this trap where they think, well, it hit the ground, Mr. Bryant, so the velocity is 0. Well, that's true. After it hits the ground, the velocity is 0. But that's not interesting, is one way to think about it. Or in that condition, the ball is no longer in free fall. Remember, it's in free fall, it's a projectile if it's only under the influence of gravity. If the ground is pushing it up, if the dirt and the grass are pushing the ball up, then it's no longer just under the influence of gravity. So what we really want to know is with what speed does it strike the ground? Not its final speed after it stops. That's 0, everyone knows that. But with what speed does it strike the ground? And so we've seen from many examples previously that whatever gravity takes away on the way up, it gives back on the way down. And so the vertical velocity at the very end is down, and it's the same as the vertical velocity at the beginning. That is 25 sine 30. So it's this same vector. It gets smaller and smaller and smaller on the way up, and then bigger and bigger and bigger on the way down, until it matches its starting speed vertically. So we might want to label that negative, huh? Because it's down. This is positive, that's to the right, that's positive, that's up, that's positive to the right, just to do that. Now we have 3 questions to solve. We want to know the maximum height, the time of flight, and the horizontal range. And so those occur, of course, at different places along the trajectory. The maximum height would occur up here, and the total time and the range would occur when the ball's over there. So what I suggest to students is they make actually 2 sets of data. We'll go ground to top, so we'll start here and end at the top. And in our second set of data, we'll go ground to ground. So from the very beginning, or at least Pat's foot, to when it strikes the ground over here. When you do that, you'll end up with 2 columns of data. Sorry, 4 columns. An X and Y for ground to top and an X and Y ground to ground. And that helps you keep things separate and organized in your mind. So I really want you to do that on your paper as you're working this with me. So let's do from ground to top. That'll help us get the maximum height first. That was the very first question. Well, we don't know the horizontal displacement from the ground to the top, but we do know the horizontal speed. That's that 25 cosine 30. And we know the acceleration in the horizontal is big fat 0. In the vertical, what do we know? Well, this is what we're looking for. This delta y, this vertical displacement, that is the maximum height. And so, am I off screen? I hope I'm not. Maybe I was. So in the horizontal, I'm gonna say that again and slow. The average horizontal speed is at 25 cosine 30. It never changes all the way across because the acceleration horizontally is 0. In the vertical, we're looking for that delta y. We're looking for that maximum height. The initial vertical velocity is no longer 0. It was in all our previous work. But now, we have a vertical velocity to start with, 25 sine 30. The acceleration is down, so minus 9.8. The final vertical speed, what's the final vertical speed at the top? Well, that's 0. And we don't know the time. So we have our data now set for ground to top. And we'll have to look at that data on the next slide to figure out the maximum height. If we go from the very bottom, the very start, to the very end, back at the ground again, then we have a different set of data. Now, one of the things I'm looking for is this horizontal distance. The horizontal speed is still the same, 25 cosine 30. Acceleration is still 0. And the time, well, the time from ground to ground, that's also something that I'm looking for. In the vertical, what's the vertical displacement from ground to ground? That's 0, isn't it? It starts on the ground and it ends on the ground, so the displacement is 0. The initial vertical speed is 25 sine 30, and that's positive, it's up. But the final vertical speed is down, minus 25 sine 30, back at the ground all the way across. And the acceleration is minus 9.8. And the time is something that we're looking for again. So now I think we have both sets of data for 2 different positions, ground to top and ground to ground. I've used that ground to top data over here. That's just finding the maximum height. So let's look at the left side first. And we're using the y data for that, the vertical part. It turns out we have an equation that doesn't have time in it, and we have enough data just in the vertical information without using the horizontal at all to solve this question, because We know the final vertical speed at the top is 0. We know the initial vertical speed is 25 sine 30, positive. We know the acceleration is negative 9.8. And we're looking for delta y, that vertical displacement. So I found this tool on my equation card. V squared equals v naught squared plus 2a delta y. And I started plugging in my known. So here's my equation and my substitution and then my solving. You might want to write that down and then try to solve it yourself and make sure you can get that answer at the bottom. So just under 8 meters, which is reasonable. And then that's for the maximum height. But for the time of flight and the range, I went with the other set of data from ground to ground. And so I've copied that over here again. And one way to find the time is just to look at the vertical information, because I have an equation with acceleration, original velocity, final velocity, and time in it. That's this one, a equals vf minus vo over t. And I substitute there and I found the time. Once I know the time, of course, we can use that little trick where the time's the same in both columns, right? So it spends the same amount of time moving vertically as it does horizontally, and I found that time, I use it over here in the horizontal part. And I use this equation again, the average is delta x over t, and I plugged in my data, and the time I got from the other answer, and I got the range to be about 55.2 meters for the horizontal. So these are the solutions there to that question. If I was you and I was watching this video at home or in class or in the library, I would try to work that out myself and make sure that you get the same answer. If you have trouble with that, this would be a perfect thing to write down and say, hey, I need to ask Mr. Bryan about this tomorrow in class, and I'll help you with it. So just to review, what we've previously done for our projectile motion problems, we've sketch labeled a trajectory, givens and unknowns in the XY chart, equation, substitute, solve, time is the same in both, and then we do our answer checks, right? So is the magnitude reasonable? Do we have units? Is the direction necessary? Those types of things. The new things that we're adding with the projectiles launched at angles is that we also label the velocity components at those positions that we know something about, the beginning, the top, maybe the very end. And in the XY chart, it may be necessary to do multiple XY charts because you may want to know something about different positions in the trajectory, so like we did today. So those are the new things that we added.